Thermodynamics processes. In this video, I'll be talking about the thermodynamic processes. Here, in this animation, we can see a piston moving inside a cylindrical container. What happens here is the equilibrium state of the thermodynamic process keeps on changing, and while the pressure and volume passes through many values, all the state it passes through may not be in equilibrium. So it has to go through some non-equilibrium states in order to attain the final equilibrium state. That is when the piston comes to the final resting position. Now, quasi-static process. So, as we have already seen, non-equilibrium states of a system are difficult to deal with. It is therefore convenient to imagine an idealized process in which at every stage the system is an equilibrium state. So in thermodynamics, a quasi-static process is a thermodynamic process that happens slowly enough for the system to remain in internal equilibrium. In this video, we will be considering the case of quasi-static process in our analysis. So in a quasi-static process, at every stage, the difference in the pressure of the system and external pressure is infinitesimally small. The same is true of the temperature difference between the system and its surroundings. A quasi-static process is obviously a hypothetical construct. In practice, processes that are sufficiently slow and do not involve accelerated motion of the piston, large temperature gradient, etc. are reasonably approximation to an ideal quasi-static process. Now we shall see isothermal process, a process in which the temperature of the system is kept fixed through a is called an isothermal process. The expansion of a gas in a metallic cylinder placed in a large reservoir of fixed temperature is an example of an isothermal process. For an isothermal process, the ideal gas equation gives PV is equal to constant, where P and V are the pressure and volume of the gas. Now for an ideal gas, the internal energy depends only on temperature. Thus, since in an isothermal process, there is no change in internal energy as there is no temperature change. So if we apply the first law of thermodynamics, which is delta Q is equal to delta W plus delta U, and here delta U is equal to 0, we will get delta Q is equal to W. That is total quantity of heat is converted to work. So in an isothermal process, W can be derived to be RT into log of the ratio of V2 by V1, where V2 is the final volume and V1 is the initial volume. In case of an isothermal expansion, V2 will be greater than V1. Hence, work done will be positive. That is, the gas absorbs heat and does work. While in an isothermal compression, V2 is lesser than V1 and hence work done is negative. That is, work is done on the gas by the environment and heat is released. Now, adiabatic process. In an adiabatic process, the system is insulated from the surroundings and heat absorbed or released is zero. The first law of thermodynamics, if we apply in this case, implies that work done by the gas results in decrease in its internal energy. Since delta Q is equal to 0, delta W is equal to minus delta E. So for adiabatic process of an ideal gas, PV raised to gamma is equal to a constant, where gamma is the ratio of specific heats at constant pressure Cp and at constant volume Cv. That is, gamma is equal to Cp divided by Cv. Now the work done in an adiabatic process can be derived to be W is equal to R divided by gamma minus 1 into T2 minus T1. So if work is done on the gas, temperature rises. That is T2 greater than T1. And if work is done by the gas, temperature decreases. That is T1 greater than T2. Now this is an example of an adiabatic process in which a tire is getting deflated. In this case, the work is done by the gas and hence the temperature of the system decreases. Now isochoric process. That is, isochoric process is a thermodynamic process in which the volume remains constant. The heat absorbed by the gas goes entirely to change its internal energy and its temperature. Here the work done is 0, or delta Q is equal to delta U. Example of this process is if we consider a gas-filled cylinder fitted with a piston when heated and the volume is kept constant, then there will be no work done. Whatever the heat is added will be used to increase the internal energy of the system. Now isobaric process. Isobaric process is a thermodynamic process in which the pressure remains constant. Work done by the gas is given by W is equal to P into V2 minus V1 is equal to mu into R into T2 minus T1, where T2 and V2 are the final temperature and volume, and V1 and T1 are the initial volume and temperature. So the heat absorbed goes partly to increase the internal energy and partly to do work. The example for an isobaric process is boiling water in an open pot, which is at atmospheric pressure. When the water boils, it changes to steam, and this steam expands, and since it is not contained, it stays at atmospheric pressure. So the pressure remains constant, but energy changes. Now cyclic process. A process in which the system will come back to its initial state is called cyclic process. In the case of a cyclic process, the resultant change in internal energy is 0. By first law of thermodynamics, the total heat absorbed equals the work done by the system. Examples in which this cyclic process takes place are in the case of heat engines and heat pump. So this is the end of this video. In this video, I have discussed the thermodynamic processes. If you have got any doubt in any of the concepts discussed in this video, please comment in the section below this video. Thank you.